Deep Learning, Machine Learning and Data Analytics Explained. Written by David Feldspar. Narrated by Jason R. Gray. Introduction. Deep learning is a new area of machine learning research, which has been introduced with the objective of moving machine learning closer to one of its original goals, artificial intelligence. Deep learning is not only a massive buzzword spanning business and technology, but also a concept that will transform most industries and jobs, as well as the way we live our lives. Data mining and analytics have played an important role in knowledge discovery and decision-making and supports in the process industry over the last several decades. As a computational engine to data mining and analytics, machine learning serves as a basic tool for information extraction, data pattern recognition, and predictions. From the perspective of machine learning, this paper provides a review on existing data mining and analytics applications in the process industry over the past several decades. The state-of-the-art of data mining and analytics are reviewed through 8 unsupervised learning and 10 supervised learning algorithms, as well as the application status of semi-supervised learning algorithms. Several perspectives are highlighted and discussed for future researches on data mining and analytics in the process industry. In recent years, many unions or countries have announced a new round of development plans in manufacturing. For example, the European Union proposed 20-20-20 goals to achieve a sustainable future, which means 20% increase in energy efficiency, 20% reduction of CO2 emissions, and 20% renewables by 2020. Those goals can only be realized by incorporating more intelligence into industrial manufacturing process. The U.S. government has proposed a new industrial internet framework for developing the next generation of manufacturing. Japan announced a revitalization plan for manufacturing. Germany proposed the concept of Industry 4.0, the main aim of which is to develop smart factories for producing smart products. Similarly, China has announced a new manufacturing plan more recently, which is known as China Manufacturing 2025, the aim of which is to also make the manufacturing process more intelligent. As an important part of manufacturing, the process industry needs to be reformulated in the era of new information technologies. How to improve process understanding and accumulate effective knowledge plays an important role in all aspects of the process industry, such as sustainability design, system integration, advanced process and quality control, decision supports, etc. From the viewpoint of automation, data mining and analytics may serve as a basic tool to promote the process industry from machine automation to information automation, and then to knowledge automation. In the past several decades, a large amount of data has been achieved in the process industry due to the wide use of distributed control systems. While it becomes more and more difficult to build first-principle models in those increasingly complex processes, data-driven process modeling, monitoring, prediction, and control have received much attention in recent years. At the very beginning, those large amounts of data have rarely been used for detailed analysis, which are instead only used for routinely technical checks and process log fulfillments. Later, awareness of the importance in extracting information from data has taken a leading role in the process industry. At the same time, the technical development of database and data analysis has been in a fast pace during those years. Therefore, research on data mining and analytics in the process industry has become quite popular since then. By analyzing the patterns of process data and relationships among variables, useful information can be extracted, based on which statistical models can then be developed for various applications, such as process monitoring, fault diagnosis, mode clustering, soft sensing of key variables and quality variables, etc. In a word, the main aim of data mining and data analysis is to extract useful information from process data. and transfer it to effective knowledge for improvement of understanding and decision supports of the process. To effectively carry out data mining and analytics in the process industry, machine learning algorithms have always played an important role. There are 4 different types of machine learning algorithms, termed unsupervised learning, supervised learning, semi-supervised learning, and reinforcement learning. While reinforcement learning is used in robotics, gaming, and navigation areas, other 3 types of machine learning have all been widely used for data mining and analytics in the process industry. According to the introduction provided by Wikipedia, machine learning is a subfield of computer science that evolved from the study of pattern recognition and computational learning theory in artificial intelligence. However, the theory of probability and statistics also plays a very important role in modern machine learning. Machine learning explores the study and construction of algorithms that can learn from and make predictions on data. In 1959, Arthur Samuel defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. And later, Tom M. Mitchell provided a widely quoted, more formal definition. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Compared to other definitions, this definition is more notable. Since its definition, machine lots of attention in various areas, such as pattern recognition, industrial applications, bioinformatics, image analysis, etc. Although the research of machine learning sunk for several times, the ship has been resailed and will become increasingly more powerful since we entered the 21st century. During the last several decades, machine learning has been playing an important role in constructing experience-based models from process data, based on which useful information can be extracted, new patterns of data can be identified, predictors can be made more easily for new data samples, decisions can be made more quickly and effectively, etc. All these applications of machine learning have fundamentally changed the manufacturing style of the process industry. For data mining and analytics in the process industry, lots of work has been reported in the past years. Among them are several reviews and books which have provided more detailed state-of-the-art of the research on this topic. However, there exists no such report that details data mining and analytics from the viewpoint of machine learning, although the terminology has been mentioned many times in various papers and books. The first aim of this paper is to provide a systematic review on data mining and analytics in the processing industry up to date from the viewpoint of machine learning. This will include reviews of topics of unsupervised learning, supervised learning, and semi-supervised learning methods for applications in the process industry. Under each specific review topic, various applications of machine learning algorithms will be introduced, with detailed discussions among different methods. The second aim of this paper is to provide new perspectives for future application of machine learning algorithms in the process industry. With the rapid development of the modern industry, new phenomena of process data have emerged. For example, the big data problem, which need to be carefully addressed when applying machine learning methods. On the other hand, the technology of machine learning itself continues to evolve all the time. For example, neural networks have been used for data mining for many years. With the increased computing power, we can create neural networks with many layers, which is known as deep learning neural networks. Both the change in industry environments and the increased power of modern technologies have made the application of machine learning more challenging, more exciting, and thus need more future investigation and more ambitious researchers to explore in this area. 10 ways predictive analytics can help the banking sector. Here are the 10 ways in which predictive analytics is helping the banking sector. 1. Fraud detection. Fraud is becoming an area of big concern for every sector and for banking and financial firms it can cost a lot to them. For individuals, it's even more dangerous because they are at risk of losing their identity in the first place. Digitization has paved the way for cybercriminals to commit more frauds. Thus, banks need intelligent systems and tools to deal with them. Predictive analytics, machine learning, big data, data mining, and stream computing are a few of the tools that are helping to catch these frauds. Analytics can be used to recognize frauds that are not very obvious, and then predictive analytics can be implemented on them to analyze them further. Data integration, utilizing unstructured data and machine learning techniques like supervised and unsupervised learning, can help detect fraud cases by following a pattern. 2. Application screening. Predictive analysis in banking can help process huge volumes of applications without excluding important variables, without delays or errors, without growing tired, all of it with regularity and steadiness. The results are very much accurate and authentic to be used, so ultimately, there doesn't have to be a comparison between traditional or manual screening and analytics. 3. Customer acquisition and retention. Predictive analytics help in the process for optimized targeting, making it easier for banks to instantly identify the high-value customer segments most likely to respond. The customer base can further expand by acquiring the right type of customer. Based on a report, it was seen that the banks that adopted predictive analytics had an increase of about 10% in new customer opportunities over a year. Also, predictive analytics helps banks and financial institutions retain their customers. It identifies the customers most likely to defect before they end the relationship. It keeps the right customers longer, and it predicts which actions will earn their loyalty. Applying this technology would also help discover the churn patterns and develop profiles of users who have left, to get an insight of why they left and discover strategies to keep them satisfied. Customer retention is another area where banks need to focus more today in order to reduce customer sapping. Loyal customers need to be rewarded, and customer attrition needs to be minimized. Sometimes it gets too late to retain a customer because they tend to have a large customer base and, hence, lose track of them. It's easy to look out for a new customer, but the old ones are always valuable. Predictive analysis helps identify which customers are willing to switch to any other bank and the reason behind their decision. It examines customer service performance, spending, past service, and other behavior patterns to predict the likelihood of a customer wanting to stop its services anytime in the near future. 4. Knowing customer buying habits. Targeting the right product and tracking customer usage is a challenge before banks, which they independently and in conjunction with retailers are trying to curb. With predictive analytics, banks can rapidly segregate various customer segments and replace it with highly relevant, individualized messages tailored to each customer's profile, resulting in a higher response rate. This ultimately helps deliver the right product to the right person. As in, if someone who has a history of buying gadgets, then the sale of high-end gadgets could be targeted at him, and in fact he would be happy to get such updates. 5. Cross-selling. Efficient cross-selling of products can happen by analyzing the existing customer behavior at places where multiple products are offered. Which specific products are to be sold to whom, hence predicting the outcome, is what successful cross-sellers do. And all of this results in more effective cross-selling, thus increasing profitability and strengthening the customer relationship. Today, securing one profitable customer is a big task for banks. Hence, cross-selling another product to an existing customer helps a lot. Predictive analytics helps examine customers' usage, spending, and other behavior, and leads to effective cross-selling of the right product at the right time. 6. Collections. Banks have a mix of customers who always pay on time and those who lag. It is a tricky task to keep track and maintain records of all individuals and differentiate who to focus on more. Predictive analytics offers clear benefits in this area. Banks can obtain a better understanding of their portfolio risk and thus improve the productiveness of the collections process. Most importantly, analytics helps identify the customers who would be at risk in the future and what actions banks should take to achieve positive results. 7. Better cash and liquidity planning. Predictive analytics can help banks track the past usage patterns and the daily coordination between the in and out payments of their branches and ATMs, hence predicting the future needs of their potential customers. Optimal management of liquid assets can result in their extra income, and a proper analytics plan can help obtain an overview of future changes in investment and liquidity options. 8. Marketing optimization. Predictive analytics helps marketers to plan marketing campaigns and programs and monitor the results closely. By providing an insight into customer behavior and attitudes and a complete current view of your customers, analytics help your marketing team deliver the right message at the right time to the right customers. 9. Customer lifetime value. Customers' lifetime value is how long the organizations are able to retain their customers. Identifying who the best customers are, making them better in different ways, and once you win them over, securing their loyalty, are a few areas that banks are focusing on. Predictive analytics helps know which customers should be the focus of new customer engagement efforts, identify the previous factors that enhanced returns on customer engagements in the past, and use that knowledge to understand why customers responded to certain messages and promotions. 10. Feedback management. Feedback management is really important. Predictive analytics allows banks and financial firms to keep up their relationship with the customers by giving them the right services and products for their need, and matching individual preferences in the most sorted way. Applications for machine learning in finance. Let's now look at how machine learning is impacting elements of the financial sector. Fraud prevention. Financial service providers have no greater responsibility than protecting their clients against fraudulent activity. Financial fraud costs Americans alone $50 billion annually. Old ways of keeping clients' accounts secure are no longer good enough. With each advancement in data security, criminals have stepped up to the challenge. To protect clients' data from increasingly sophisticated threats, institutions and companies must stay one step ahead of the hackers. Machine learning enables applications to thwart security breaches by outthinking the criminals. By comparing each transaction against account history, machine learning algorithms are able to assess the likelihood of transactions being fraudulent. Unusual activities, such as out-of-state purchases or large cash withdrawals, raise flags that can cause the system to introduce steps to delay the transaction until a human can make a decision. In many cases, depending on the nature of the attempted transaction, a purchase or withdrawal attempt may be automatically declined by the system. Unlike a human agent, the algorithm is able to quickly weigh the transaction details against thousands of data points and make a determination whether or not the attempted activity is uncharacteristic of the account owner. And unlike non-AI software, machine learning programs learn from each action the account owner takes, and from each decision the software makes. Over time, the algorithms adjust themselves in response to changing habits on the part of the account owner. In order for machine learning to be effective, it must be able to quickly access and digest large amounts of data. Realizing the value of machine learning, Amazon, Microsoft, IBM, and Google are each integrating machine learning capabilities into their cloud-based developer interfaces. As criminals become more advanced in their strategies, only computer systems with access to big data and with the ability to think and learn will be able to stop them. Risk management. It should come as no surprise that machine learning technology can be a powerful ally in the quest for better risk management. While traditional software applications predict creditworthiness based on static information from loan applications and financial reports, machine learning technology can go further and also analyze the applicant's financial status as it may be modified by current market trends and even relevant news items. By applying predictive analysis to huge amounts of data in real time, machine learning technology can detect rogue investors working in unison across multiple accounts, something that would nearly be impossible for a human investment manager. Efficiency is another benefit of machine learning. By assuming a substantial amount of the burden to monitor accounts, machine learning systems enable investment managers to focus on more productive tasks, such as servicing clients. Investment predictions. Computer-aided trading services have been around for some time. They allow investors to have an order placed when a stock reaches a predetermined price, and to sell when that price drops below a certain limit. By automating functions, such platforms make trading easier for large and small investors alike. While they can even make recommendations based on automated analysis of market trends, they have limitations. In recent years, hedge funds have increasingly moved away from traditional predictive analysis methods and have adopted machine learning algorithms for predicting fund trends. Using machine learning, fund managers hope to identify market changes earlier than is possible with traditional investment models. The potential of machine learning technology to disrupt the investment banking industry is being taken seriously by major institutions. J.P. Morgan, Bank of America, and Morgan Stanley are developing automated investment advisors powered by machine learning technology. Wise fintech companies will likely follow suit. Customer service. Poor customer service remains one of the chief complaints among consumers, regardless of the industry. Originally, the complaint centered on slow customer service, but with the universal utilization of automated phone support, customers are frustrated by not being able to talk to a human. For the innovative financial service company willing to invest in machine learning technology, this should not represent a problem so much as an opportunity. The advantages of automated customer support systems include directing the customer to the correct department, giving them the option to resolve minor problems using the automated interface, and keeping the customer from having to wait for someone to answer the phone, all without human interaction. The company benefits by not paying salaries to personnel who would handle these tasks, and the customer supposedly benefits by having their problems handled with the expeditiousness of modern computers. In theory, anyway. In reality, many customers do not benefit from automated customer service when their problem is uncommon and not represented by a numeric option. While definitely an improvement, voice recognition often still fails to accommodate the unusual request, with, quote, "I'm sorry I'm not understanding you, please hold for assistance," unquote, being the stock response to a customer with a unique problem. The solution, as provided by machine learning technology, is not to replace automated customer support systems, but to make them better. The tremendous power of machine learning technology to access data, recognize patterns, and interpret behavior means that the technology can be used to create automated customer support systems that mimic a human agent, with the ability to understand and respond to uncommon concerns. By making phone and online customer support portals more human-like, financial institutions can provide efficient support that reduces customer blowback. Additionally, machine learning technology can help customers make better product selections by weighing previous account activities against current data provided by the client and from elsewhere. Product or service recommendations can be made directly to the client or through a financial advisor. The result is a better informed client whose time is not wasted by inappropriate offerings. One of the most important paybacks for companies that invest in machine learning customer service is the ability to better understand the needs of each individual customer, which is always a good thing. No company, fintech or fish market, operates without sound management. And for management to be sound, it must function effectively and efficiently. Machine learning technology, perhaps surprisingly, can help executives and managers to perform their jobs with greater ease than ever before. We are talking about digital assistants, and the competition to develop a winning platform is fierce. Google, Apple, Facebook, and Microsoft all have their own version of the virtual secretary. Google's Allo, Apple's popular Siri, Facebook's M, and Microsoft's Cortana currently represent the state-of-the-art in digital helpers. Each targets a certain market, and each has its own advantages and limitations. For the innovative fintech startup intent on making its own toys, it is a good time to consider the competition and then take away what will work best in the business office of a financial institution. Machine learning technology includes several functionalities that can be useful for developing a custom digital assistant, namely speech recognition, access to big data, powerful data analytics capabilities, the ability to integrate with social media, email, and third-party applications and platforms, and pattern and behavior recognition. Although this list is far from inclusive, it is easy to see how machine learning technology can replace certain executive duties while augmenting others. Whether a financial service company chooses to invest in the development of a virtual assistant platform for its own operation, or for the purpose of offering the platform as part of a service package for their clients, the return on investment is likely to be substantial. Marketing. Having read of the many ways in which machine learning can help keep accounts secure, improve risk management, and offer investment strategies, you might not expect the technology to also be a good marketing tool. On the contrary, the ability to make predictions based on past behaviors is fundamental to any successful marketing effort. By analyzing web activity, mobile app usage, and response to previous campaigns, machine learning software can predict the effectiveness of a marketing strategy for a given customer. With the online marketing power of Google now augmented by machine learning, it is possible for developers working in the financial sector to create smart tools that make the job of marketing executives easier than ever. The potential of machine learning to supercharge the marketing industry has led to a spurt in machine learning-based advertising startups in the last year. So many, in fact, that 2015 saw no less than 10 acquisitions in this space, including the Twitter acquisition of Telepart for more than $530 million. Clearly, big money has its eye on machine learning as the next big thing in marketing. Network security. Among the top considerations for any network administrator or data security professional is how to recognize suspicious patterns occurring across their networks. The challenge to identify such patterns lends itself perfectly to the capabilities of machine learning. The power of intelligent pattern analysis, combined with big data capabilities, certainly gives machine learning technology an edge over traditional non-AI tools. One might go so far as to declare machine learning as the last hope of securing critical networks against professional and state-sponsored cyber attacks. Despite costly and increasingly complex IT security platforms against modern cyber attacks, so far, Hackers have breached the network security of such mammoths as the U.S. Department of Justice, the U.S. Democratic National Committee, or DNC, the Internal Revenue Service, Snapchat, LinkedIn, and Oracle. Clearly, organizations need to rethink their approach to cybersecurity. Existing systems do not necessarily need to be abandoned, but the additional layer of wizardry which machine learning security can provide is the next step in the evolution of network security. Adding credence to the notion that machine learning is a viable network security tool, Microsoft is investing heavily in its own deterministic machine learning big data platform. Using statistical analysis of baseline metrics along with historical data from bad behaviors, computer scientists are constructing models that can identify anomalous or abnormal behaviors. While not every organization replicates the resources of IBM, the lessons learned from the tech giant will help fuel independent development in the fintech, financial, IT security space. How Ignite can help. To foresee all the ways in which machine learning will impact the financial sector would require the highly sought-after and yet unperfected technology, the crystal ball. For the lack of it, we can only envision how the technology can be used to solve problems now and in the near future. The 7 applications we have discussed surely represent a technology in its infancy. No doubt, innovative fintech startups are already adding to the list. As a financial service provider, finding fresh, innovative ways of serving your clients and customers is key to your longevity, and knowing how to access and use big data is only the start. Today's landscape demands that you do more. You must bridge new technology with systems that are familiar to your users, while improving the level of service minute by minute. That's where Ignite outsourcing comes in. Deep learning in data mining and machine learning. The main concept in deep learning algorithms is automating the extraction of representations, or abstractions, from the data. Deep learning algorithms use a huge amount of unsupervised data to automatically extract complex representations. These algorithms are largely motivated by the field of artificial intelligence, which has the general goal of emulating the human brain's ability to observe, analyze, learn, and make decisions, especially for extremely complex problems. Work pertaining to these complex challenges has been a key motivation behind deep learning algorithms, which strive to emulate the hierarchical learning approach of the human brain. Models based on shallow learning architectures, such as decision trees, support vector machines, and case-based reasoning, may fall short when it useful information from complex structures and relationships in the input corpus. In contrast, deep learning architecture's ability to generalize in non-local and global ways, generating learning patterns and relationships beyond immediate neighbors in the data. Deep learning is, in fact, an important step towards artificial intelligence. It not only provides complex representations of data, which are suitable for AI tasks, but also makes the machines independent of human knowledge, which is the ultimate goal of AI. It extracts representations directly from unsupervised data, without human interference. A key concept underlying deep learning methods is distributed representations of the data, in which a large number of possible configurations of the abstract features of the input data are feasible, allowing for a compact representation of each sample, and leading to a richer generalization. The number of possible configurations is exponentially related to the number of extracted abstract features. Noting that the observed data was generated through interactions of several known or unknown factors, and thus, when a data pattern is obtained through some configurations of learned factors, additional unseen data patterns can likely be described through new configurations of the learned factors. Compared to learning based on local generalizations, the number of patterns that can be obtained using a distributed representation scales quickly with the number of learnt factors. Deep learning algorithms lead to abstract representations because more abstract representations are often constructed based on less abstract ones. An important advantage of more abstract representations is that they can be invariant to the local changes in the input data. Learning such invariant features is an ongoing major goal in pattern recognition. For example, learning features that are invariant to the face orientation in a facial recognition task. Beyond being invariant, such representations can also disentangle the factors of variations in the data. The real data used in AI-related tasks mostly arises from a complicated interaction of many sources. For example, an image is composed of different sources of variations, such as light, object shapes, and object materials. The abstract representations provided by deep learning algorithms can separate the different sources of variations in the data. Deep learning algorithms are actually deep architectures of consecutive layers. Each layer applies a nonlinear transformation on its input and provides a representation in its output. The objective is to learn a complicated and abstract representation of the data in a hierarchical manner, bypassing the data through multiple transformation layers. The sensory data, for example pixels in an image, is fed to the first layer. Consequently, the output of each layer is provided as input to its next layer. Stacking up the nonlinear transformation layers is the basic idea in deep learning algorithms. The more layers the data goes through in the deep architecture, the more complicated the nonlinear transformations which are constructed. These transformations represent the data, so deep learning can be considered as a special case of representation learning algorithms, which learn representations of the data in a deep architecture with multiple layers of representations. The achieved final representation is a highly nonlinear function of the input data. It is important to note that the transformations in the layer of deep architecture are nonlinear transformations which try to extract underlying explanatory factors in the data. One cannot use a linear transformation like PCA as the transformation algorithms in the layer of deep structure, because the compositions of linear transformations yield another linear transformation. Therefore, there would be no point in having a deep architecture. For example, by providing some facial images to the deep learning algorithm, at the first layer, it can learn the edges in different orientations. In the second layer, it composes those edges to learn more complex features, like different parts of a face, such as lips, noses, and eyes. In the third layer, it composes those features to learn even more complex features, like face shapes of different persons. These final representations can be used as the feature in applications of facial recognition. This example is provided to simply explain in an understandable way how a deep learning algorithm finds more abstract and complicated representations of data by composing representations acquired in a hierarchical architecture. However, it must be considered that deep learning algorithms do not necessarily attempt to construct a predefined sequence of representations at each layer, such as edges, eyes, faces, but instead more generally perform nonlinear transformations in the different layers. These transformations tend to disentangle factors of variations in data. Translating this concept to more appropriate training criteria is still one of the main open questions in deep learning algorithms. The final representation of data constructed by the deep learning algorithm, or output of the final layer, provides useful information from the data, which can be used as features in building classifiers, or even can be used for data indexing and other applications which are more efficient when using abstract representations of data rather than high-dimensional sensory data. Learning the parameters in deep architecture is a difficult optimization task. such as learning the parameters in neural networks with many hidden layers. In 2006, Hinton proposed learning deep architectures in an unsupervised, greedy, layer-wise learning manner. At the beginning, the sensory data is fed as learning data to the first layer. The first layer is then trained based on this data, and the output of the first layer, the first level of learned representations, is provided as learning data to the second layer. Such iteration is done until the desired number of layers is obtained. At this point, the deep network is trained. The representations learned on the last layer can be used for different tasks. If the task is a classification task, usually another supervised layer is put on top of the last layer, and its parameters are learned, either randomly or by using supervised data and keeping the rest of the network fixed. At the end, the whole network is fine-tuned by providing supervised data to it. Here, we explain two fundamental building blocks: unsupervised single-layer learning algorithms, which are used to construct deeper models, autoencoders, and restricted Boltzmann machines, RBMs. These are often employed in tandem to construct stacked autoencoders, and deep belief networks, which are constructed by stacking up autoencoders and restricted Boltzmann machines, respectively. Autoencoders, also called autoassociators, are networks constructed of three layers: input, hidden, and output. Autoencoders try to learn some representations of the input in the hidden layer in a way that makes it possible to reconstruct the input in the output layer based on these intermediate representations. Thus, the target output is the input itself. A basic autoencoder learns its parameters by minimizing the reconstruction error. This minimization is usually done by stochastic gradient descent, much like what is done in multilayer perception. If the hidden layer is linear, and the mean squared error is used as the reconstruction criteria, then the autoencoder will learn the first k principal components of the data. Alternative strategies are proposed to make autoencoders nonlinear, which are appropriate to build deep networks as well as to extract meaningful representations of data, rather than performing just as a dimensional reduction method. Bengio et al. Have called these methods regularized autoencoders, and we refer an interested reader to that paper for more details on algorithms. Another unsupervised single-layer learning algorithm, which is used as a building block in constructing deep belief networks, is restricted Boltzmann machine, RBM. RBMs are likely the most popular version of Boltzmann machine. They contain one visible layer and one hidden layer. The restriction is that there is no interaction between the units of the same layer, and the connections are solely between units from different layers. The contrastive divergence algorithm has mostly been used to train the Boltzmann machine. 5 steps to implementing unsupervised big data machine learning. There is quite a buzz around unsupervised machine learning for asset maintenance, for good reason. Unsupervised machine learning provides the benefits of the digital twin, or real-time alerts to emerging asset degradation and failure based on analysis of sensor data. At the same time, unsupervised machine learning does not come with the hefty price tag, because the advanced AI algorithm can analyze vast amounts of data in the cloud and is sensor agnostic. Big data machine learning, both supervised and unsupervised, are at the forefront of the move to the smart factory. Industrial plants now recognize that only a fraction of their existing SCADA data is ever used for condition-based monitoring. Furthermore, because controls are manually set, only breaches of control limits are monitored. The result is that the emerging failures are typically ignored until it is too late and the CBM control limits have been exceeded. Unsupervised big data machine learning for asset maintenance. There are 5 discrete steps required for using unsupervised machine learning for asset maintenance. sensor data generated and stored. Raw sensor data is generated and transmitted to the historian database. Data streamed to the Procesno cloud. All raw sensor data is continuously streamed from the local historian database to the Procesno cloud, whereas condition-based monitoring only monitors a few critical sensors. There are no limits to the number of sensors that can be monitored by Procesno. AI-driven anomaly detection. Whereas CBM tracks breaches of manually set control limits, the Procesno Advanced AI algorithm detects anomalies in data patterns. The algorithms are sensor agnostic. They are looking for abnormal data patterns to identify emerging degradations and machine failure. Contextualization of machine behavior. Detecting abnormal sensor data behavior is insufficient. Procesno's algorithm searches for correlations and patterns between sensors, even if they are seemingly unrelated. Once emerging patterns are detected, the facility owner receives an alert of potential failure. Included in an alert is information that provides insights into the failure origin. Which historian databases can be used for unsupervised machine learning? The following is a partial list of the historian databases that can be accessed by the Procesno Unsupervised Machine Learning Cloud. OSIsoft PI Historian, AspenTech Info Plus Historian, Emerson Ovation or Delta V, Schneider Electric Wonderware SITTech Historian, GE Digital, formerly Proficiency, ABB Decathlon, SAP HANA, Siemens Simatic, Honeywell Historian, MS SQL, and Oracle. Comparing supervised versus unsupervised machine learning. There has been much discussion about supervised machine learning, especially given the significant investments in the GE Predicts platform and Siemens MindSphere. Supervised machine learning is used by the digital twin. It is called supervised because the algorithm needs access to the data labels of historic downtime records. In the digital twin, a complete and accurate 3D modeling using the asset's blueprints is needed. Once the digital twin is created, the learning algorithm can learn the workings of the machine to be able to duplicate its behavior. Unsupervised machine learning is sensor and asset agnostic. With unsupervised learning, there is no need to understand the physical working of the machine, because the algorithm seeks to detect abnormal data patterns. Because there are few limitations to the amount of sensor data analyzed, an entire factory can be monitored. Ultimately, the differences between supervised and unsupervised model impact price, speed to market, and the number of assets that can be monitored. How machine learning can optimize finance processes. Machine learning is becoming a buzzword in nearly every industry today, and finance is no exception. As its applications and capabilities grow, machine learning is powering finance departments towards the next generation of digitization. Here are 3 ways finance professionals can embed machine learning to boost the maturity of their financial management systems or extend their accounting and reporting capabilities to better meet today's business challenges. Embrace digitization in your finance strategy. Before finance departments can unlock the value of machine learning, they must first ensure that digital tools are at the core of their operations. Machine learning depends on live business and big data being integrated across the organization, which is possible to aggregate in real time only through digital in-memory applications based on a modern ERP platform. With a recent survey showing that nearly 1 in 5 small and mid-sized enterprises today are not using accounting software at all, many businesses are still a step behind in being able to apply more advanced technologies. As new technology makes it easier for finance departments to adopt digital infrastructure that is connected, intelligent, responsive, and predictive, They can also take advantage of machine learning to further improve business performance. Along with digital solutions for managing large amounts of data, machine learning becomes a natural next step to increase efficiency and improve business performance. Use automation where it counts. In today's workplace, finance professionals are spending just 17% of their time on strategic activities, with a lack of automation serving as the culprit for much of this inefficiency. As finance teams move away from managing work through spreadsheets and towards digital and cloud ERP solutions, machine learning can provide an additional edge in driving innovation through the finance function. Digital finance solutions that incorporate machine learning capabilities can greatly expedite transactional tasks and bring teams closer to eliminating manual administrative work entirely. Financial professionals can increase the time spent on strategic priorities by automating back-office processes like procure to pay, order to cash, and record to report. Machine learning programs utilize predictive algorithms to churn through massive amounts of data, working at a much faster speed than traditional processes dependent on human input. Turning non-strategic tasks over to computers will allow corporate finance professionals to spend time on more rewarding and higher value work, like business or deal support or advanced analytics, which will in turn yield increased business opportunities for the entire organization. Supplement human processes with machine support. While not all financial processes can be completely automated, machine learning can help to support transactions and reduce errors in tasks that require human input. For example, it is likely that financial statement auditing will never be completely trusted to machines, as it depends on human judgment in evaluating circumstantial reasoning behind data. However, machines can be useful in using patterns in datasets to highlight potential areas of discrepancy and double-check human work. Machine learning technologies can sort through high volumes of data from financial reports at an exponentially faster pace than humans, and then turn that data over to human eyes, which can subsequently investigate the story behind the numbers and evaluate whether certain patterns or anomalies may be cause for concern. Another process that can allow finance teams to benefit from collaboration between humans and intelligent machines is fraud reduction and cybersecurity. As finance departments are embracing digital solutions for storing and managing financial data, either on-premise or in the cloud, cybersecurity is becoming a top concern for CFOs, who must ensure that access to information is monitored and regulated. Again, machines have the ability to churn through massive sets of data regarding access to and transactions upon those datasets, identifying abnormal patterns or unique access behaviors. Cybersecurity professionals in the enterprise can then analyze the data and determine the next steps that need to be taken to ensure the continual security of financial information, easing the worries of CFOs. By embracing a robust digital strategy, allowing automation to take over administrative work, and applying machine learning to supplement human processes, finance professionals can work at the speed of business today and ensure that their organizations are able to continuously innovate. As the capabilities of machine learning continue to grow, CFOs will need to ensure that their organizations are ready to unlock the full value of automation and machine learning through its many applications in accounting and finance. Thanks again for buying my book. If you have a minute, please leave a review. I take reviews seriously and always look at them. This way, you are helping me provide you better content that you will love in the future. A review doesn't have to be long, just 1 or 2 sentences and a number of stars you find appropriate. Hopefully 5, of course. Also, if I think your review is useful, I will mark it as helpful. This will help you become more known on Amazon as a decent reviewer, and will ensure that more authors will contact you with free ebooks in the future. This is how we can help each other. You can look at these books too: Data Analytics, Data Mining, and Data Science for Business. Disclaimer: the information is provided as is. The author, publishers, and/or marketers of this information disclaim any loss or liability, either directly or indirectly, as a consequence of applying the information presented herein, or in regard to the use and application of said information. No guarantee is given, either expressed or implied, in regard to the merchantability, accuracy, or acceptability of the information. The pages within this ebook have been copyrighted. What are some popular machine learning methods? Two of the most widely adopted machine learning methods are supervised learning and unsupervised learning. But there are also other methods of machine learning. Here's an overview of some of the most popular types. Supervised learning algorithms are trained using labeled examples, such as an input where the desired output is known. For example, a piece of equipment could have data points labeled either F for failed or R for runs. The learning algorithm receives a set of inputs along with the corresponding correct outputs, and the algorithm learns by comparing its actual output with the correct outputs to find errors. It then modifies the model correctly. Through methods like classification, regression, prediction, and gradient boosting, supervised learning uses patterns to predict the values of the label on additional unlabeled data. Supervised learning is commonly used in applications where historical data predicts likely future events. For example, it can anticipate when credit card transactions are likely to be fraudulent or which insurance customer is likely to file a claim. Unsupervised learning is used against data that has no historical labels. The system is not told the right answer. The algorithm must figure out what is being shown. The goal is to explore the data and find some structure within. Unsupervised learning works well on transactional data. For example, it can identify segments of customers with similar attributes, who then can be treated similarly in marketing campaigns. Or it can find the main attributes that separate customer segments from each other. Popular techniques include self-organizing maps, nearest neighbor mapping, k-means clustering, and singular value decomposition. These algorithms are also used to segment text topics, recommend items, and identify data outliers. Semi-supervised learning is used for the same applications as supervised learning, but it uses both labeled and unlabeled data for training. Typically, a small amount of labeled data with a large amount of unlabeled data, because unlabeled data is less expensive and takes less effort to acquire. This type of learning can be used with methods such as classification, regression, and prediction. Semi-supervised learning is useful when the cost associated with labeling is too high, to allow for a fully labeled training process. Early examples of this include identifying a person's face on a webcam. Reinforcement learning is often used for robotics, gaming, and navigation. With reinforcement learning, the algorithm discovers through trial and error which actions yield the greatest rewards. This type of learning has three primary components: the agent, which is the learner or decision maker, the environment, which is everything the agent interacts with, and actions, or what the agent can do. The objective is for the agent to choose actions that maximize the expected reward over a given amount of time. The agent will reach the goal much faster by following a good policy. So, the goal in reinforcement learning is to learn the best policy. Data mining. Data mining can be considered a superset of many different methods to extract insight from data. It might include traditional statistical methods and machine learning. Data mining applies methods from many different areas to identify previously unknown patterns from data. This can include statistical algorithms, machine learning, text analytics, time series analysis, and other areas of analytics. Data mining also includes the study and practice of data storage and data manipulation. Machine learning. The main difference with machine learning is that just like statistical models, the goal is to understand the structure of the data, fit theoretical distributions to the data that are well understood. So, with statistical models, there is a theory behind the model that is mathematically proven, but this requires that data meets certain strong assumptions too. Machine learning has developed based on the ability to use computers to probe the data for structure, even if we do not have a theory of what that structure looks like. The test for a machine learning model is a validation error on new data, not a theoretical test that proves a null hypothesis. Because machine learning often uses an iterative approach to learn from data, the learning can be easily automated. Passes are run through the data until a robust pattern is found. Deep learning. Deep learning combines advances in computing power and special types of neural networks to learn complicated patterns in large amounts of data. Deep learning techniques are currently state-of-the-art for identifying objects in images and words in sounds. Researchers are now looking to apply these successes in pattern recognition to more complex tasks such as automatic language translation, medical diagnoses, and numerous other important social and business problems. Supervised versus unsupervised machine learning. Data scientists use many different kinds of machine learning algorithms to discover patterns in big data that lead to actionable insights. At a high level, these different algorithms can be classified into two groups based on the way they learn about data to make predictions: supervised and unsupervised learning. Supervised machine learning is the more commonly used between the two. It includes such algorithms as linear and logistic regression, multi-class classification, and support vector machines. Supervised learning is so named because the data scientist acts as a guide to teach the algorithm what conclusions it should come up with. It's similar to the way a child might learn arithmetic from a teacher. Supervised learning requires that the algorithm's possible outputs are already known, and that the data used to train the algorithm are already labeled with correct answers. For example, a classification algorithm will learn to identify animals after being trained on a dataset of images that are properly labeled with the species of the animal and some identifying characteristics. On the other hand, unsupervised machine learning is more closely aligned with what some call true artificial intelligence. The idea that a computer can learn to identify complex processes and patterns without a human to provide guidance along the way. Although unsupervised learning is prohibitively complex for some simpler enterprise use cases, it opens the doors to solving problems that humans normally would not tackle. Some examples of unsupervised machine learning algorithms include k-means clustering, principal and independent component analysis, and association rules. While a supervised classification algorithm learns to ascribe inputted labels to images of animals, its unsupervised counterpart will look at inherent similarities between the images and separate them into groups accordingly, assigning its own new label to each group. In a practical example, this type of algorithm is useful for customer segmentation because it will return groups based on parameters that a human may not consider due to pre-existing biases about the company's demographic. When to use supervised and unsupervised data mining. Data mining techniques come in two main forms: supervised, also known as predictive or directed, and unsupervised, also known as descriptive or undirected. Both categories encompass functions capable of finding different hidden patterns in large datasets. Although data analytics tools are placing more emphasis on self-service, it's still useful to know which data mining operation is appropriate for your needs before you begin a data mining operation. Supervised data mining. Supervised data mining techniques are appropriate when you have a specific target value you'd like to predict about your data. The targets can have two or more possible outcomes, or even be a continuous numeric value. More on that later. To use these methods, you ideally have a subset of data points for which this target value is already known. You use that data to build a model of what a typical data point looks like when it is one of the target values. You then apply that model to data for which that target value is currently unknown. The algorithm identifies the new data points that match the model of each target value. Now, let's clarify that with some specific demonstrations. Classification. As a supervised data mining method, classification begins with the method described above. Imagine you're a credit card company, and you want to know which customers are likely to default on their payments in the next few years. You use the data on customers who have and have not defaulted for extended periods of time to build data, or training data, to generate a classification model. You then run that model on the customers you're curious about. The algorithms will look for customers whose attributes match the attribute patterns of previous defaulters or non-defaulters and categorize them according to which group they most closely match. You can then use those groupings as indicators of which customers are most likely to default. Similarly, a classification model can have more than two possible values in the target attribute. The values could be anything from the shirt colors they're most likely to buy, the promotional methods they'll respond to, like mail, email, or phone, or whether or not they'll use a coupon. Regression. Regression is similar to classification, except that the target attribute's values are numeric rather than categorical. The order of magnitude of the value is significant in some way. To reuse the credit card example, if you wanted to know what the threshold of debt new customers are likely to accumulate on their credit card, you would use a regression model. Simply supply data from current and past customers with their maximum previous debt level as the target value, and a regression model will be built on that training data. Once run on the new customers, the regression model will match attribute values with predicted maximum debt levels and assign the predictions to each customer accordingly. This could be used to predict the age of customers with demographic and purchasing data, or to predict the frequency of insurance claims. Anomaly detection. Anomaly detection identifies data points atypical of a given distribution. In other words, it finds the outliers. Though simpler data analysis techniques than full-scale data mining can identify outliers, data mining anomaly detection techniques identify much more subtle attribute patterns and the data points that fail to conform to those patterns. Most examples of anomaly detection uses involve fraud detection, such as for insurance or credit card companies. Unsupervised data mining. Unsupervised data mining does not focus on predetermined attributes, nor does it predict a target value. Rather, unsupervised data mining finds hidden structure and relation among data. Clustering. The most open-ended data mining technique, clustering algorithms, finds and groups data points with natural similarities. This is used when there are no obvious natural groupings, in which case the data may be difficult to explore. Clustering the data can reveal groups and categories you were previously unaware of. These new groups may be fit for further data mining operations, from which you may discover new correlations. Association. Frequently used for market basket analysis, association models identify common co-occurrences among a list of possible events. Market basket analysis is examining all items available in a particular medium, such as the products on store shelves or in a catalog, and finding products that are commonly sold together. This operation produces association rules. Such a rule could be a statement declaring 80% of people who buy charcoal, hamburger meat, and buns also buy sliced cheese. Or in a less market basket style example, 90% of Detroit citizens who root for the Tigers, the Lions, and the Pistons also favor the Red Wings over other hockey teams. Such rules can be used to personalize the customer experience to promote certain events or actions. This can be accomplished by organizing store shelves with associated items nearby, or by tracking customer movements through a website in real time to present them with relevant product links. Feature extraction. Feature extraction creates new features based on attributes of your data. These new features describe a combination of significant attribute value patterns in your data. If violence, heroism, and fast cars were attributes of a movie, then the feature may be action, akin to a genre or a theme. This concept can be used to extract the themes of a document based on the frequencies of certain keywords. Representing data points by their features can help compress the data, trading dozens of attributes for one feature. Make predictions. Data with this feature often has these attributes as well, and recognize patterns. Additionally, features can be used as new attributes, which can improve the efficiency and accuracy of supervised learning techniques, like classification, regression, anomaly detection, etc. Knowing your goals and the appropriate techniques to achieve them can help your data mining operations run smoothly and effectively. Different data is appropriate for different insights, and understanding what you're asking from your data analysis expedites the process for everyone.